DBAMA. Hello and welcome everybody to DBAMA. Today we have Norvald presenting. Norvald's the lead for the MySQL Optimizer team, and he's going to be telling us about query profiling. So Norvald, please take it away.
Thank you. So if you want to see my queries and stuff, it's on GitHub. I don't know if you can read this, but it's GitHub/nryeng, so NRYENG, and just click to find the query profiling thing.
Awesome. I'll add that to the show notes as well.
Yeah. So I won't stick to the script, I think, but it's around somewhat like the topic I'm talking about. So we have several tools for query analysis and mitigating bad plans in MySQL. So explain, you'll know, starting in MySQL 8.0 something, you have explain formal equals 3. I really recommend that one. And we have explain analyze that does some profiling of query execution, CPU profiling, showing you how much time things take. So I'm going to go through explain analyze quickly, and then we have things like optimizer trace if you want to inspect the optimizer, the choices it makes. Then we have performance schema that does a lot more. It just contains too much stuff for me to understand all of it. But I'm going to go into performance schema for some memory profiling. So we want to look at how the memory profile of the query changes during execution. And then if you find some problems, you have optimizer hints or optimizer switch to correct that for single queries, for sessions, or for the server as a whole. So I'm going to cover profiling query executions and timings. That's not where I'm going to spend most of the time, though. Most of the time will be on memory profiling, which is an experiment I've been working on for a little while. And I made it work, so it's not it should work in this demo as well. But this is something new that I've never done before. I'm just trying to graph the memory usage of a query. So that is my view on this thing. Like, other people are monitoring the server as a whole. A lot of stuff in performance schema is about monitoring the server as a whole. But I'm looking at this from a single query. I'm looking at how can I focus on that single query and what it does, how much time does it take, why does it take that much time, what is it doing, what memory is it using. So for me as a developer of the MySQL server, I'm curious about how the server behaves and maybe find bugs and find things I have to look into. But for you guys as DBAs and users, you want to see how your specific query behaves in order to tune your query. My side would be to kind of fix the bug that makes the query behave that way. But for you guys, I guess it's about tuning the query to keep within memory limits, keep within execution time limits, whatever you have. So let's just start running a very simple query. So I'm using this testdb that's here. I guess it's Giuseppe's database. I'm not going to use the whole data set. I'm just going to look at some very simple tables. So I can take this query, unsave paste, yeah, sure. So I'm selecting employees, joining them with their current department. So there's a employee table, there's a departments table, there's a table current dept emp that says who belongs to which department at this moment in time, because there's a bigger history table showing the historical assignments of people. This is a very simple join, and it produces something like employees doesn't exist. Demo effect. Oh.
You're just hitting case sensitivity.
Yeah, I know. I saw it. So there's like 300,000 or something, I think, in there. 324 people in this department. So that's the query it executes. The plan is to look at with explain format equals 3. So here you see I can do the traditional one first, which is a big table. So you see a lot of tables and things joined together. I find this tree view much easier to read because it shows me the execution path, the tree of operators we are actually executing in the server. So we see here there's a set of nested loop joins, 3 joins, and the inner one is reading from is doing a table scan on a materialized table, and that table is the materialization of this query, which is a index scan on the table link in departments and employees, and just aggregating that stuff. So it's using an index scan in order to get it in the order of the groups so that it can aggregate. And then that thing is joined with a index lookup. So this is nested loop with index lookup on the inner table. And then from that index lookup, it filters out some stuff based on date. This is where it does the is currently working in that department part. But this is much more complex than the query I presented. That's because this current department employee thing is not a table, it's a view. So it does view expansion, and we see the view actually expanded here. And then we have some other index lookups. So nested loop join is fine for these things with lookups. If you have some tables without indexes, you might see a hash join appear in there. But this is the way the server is actually set up to run these queries. Each of these lines with an arrow in front of them are an iterator. So each line is an iterator. And I have here let's close all these tabs. I have the doxgen documentation for this iterator. It's a row iterator. It returns a row. So we see here a lot of different types of iterators that we can use in the server to build up your query. And of course, it has constructor and destructor. Init is a function we call just before we start executing a query. Or if we are executing it several times, it's used also to reinitialize. The read function is the function that actually reads a row. So if I go back to this query, I'm going to start at the top. I'm calling read on this one, which calls read on its children, and it calls read all the way down until a row actually starts popping up and pops out at the top. And then there's a loop here on the top that keeps iterating and iterating and reading that's a new row until we've read enough rows to finish the query. So the limit will be applied at the end here, and then we just said end of file. So that's the way we are executing this thing. So we are calling read until we get all the rows. And kind of the magic of explain analyze, which I will show later on, is that we instrument this thing. So instead of using row iterator, we have something called a timing iterator. It's a subtype of row iterator that wraps around another iterator. So it wraps it. It doesn't do much, but it does count the number of times you call init, the number of times you call read, and records a timestamp every time you do. So that we have a timestamp from the first time you call init and read and the last time. And we also had the counts on the number of times you've done that. That gives us some statistics. It gives us a time from you start executing a query until the first row and until the last row. And it will also give us the number of rows you read, the number of reads, and the number of times we have reinitialized this query over the time. So I can replace my explain format equals 3 with explain analyze. I don't have to specify format equals 3. It's the only analyze format we support at the moment. I hope in the end we will align all these formats so that all formats show the exact same information and can be used in analyze and not analyze, but at the moment it's not. I'm afraid this old traditional format is not easy to extend to that information, so that might have to be replaced with something else. But we'll see where we end up in the end. But for now, I think the tree format is the best choice to understand the plans. I know some old timers like this traditional one, and it's there. It's well, it might go away in the end, but at the moment it works just as it used to be. So explain analyze gives us the same. Well, it waits a bit because it's actually executing a query. That's the difference. Explain doesn't actually execute a query; it dumps the plan. But explain analyze actually executes a query and does all these counting. And instead of the result, it returns the explain output. So what we see now is that we have this part attached to every iterator down here. So this, by the way, these numbers are in milliseconds. So the whole thing for last row took 4.29 seconds, which matches this number pretty well. So there are different timers counting these things. It's a different thing. I think this one is on the client side anyway, so it's some overhead there. We also see that the entire query returned 300,000 rows, and it loops once, so it's never repeated. In order to see something that is actually repeated, we have, if you go to our query, we have the innermost join that joins this materialized table with an index lookup on the department. We see that we are looping 300,024 times over this index lookup, which means we are looking up 300,024 rows, which makes sense because we're actually doing a nested loop join with an index lookup. So we have 300,000 rows on the outer table, and we are doing 300,000 lookups on this inner table. And we see each of these lookups, they return one row, so the time to the first and last row is the same thing, but it's very, very fast. While if you look at this, we can look at this one. This is time to the first row at the outermost loop we have. That's 560 milliseconds. That's half a second. And if you look at the reason for that, we see that our materialization takes that long. So materializing the first group by thing takes that long. That's why it takes so long to execute the first thing, to get to the first row. So that's where we are spending that initial time until we start actually returning rows. So we are waiting half a second before the first row arrives. And then, of course, because of the data and all the joining, we spend 3.5 more seconds actually executing the joins and joining stuff. But until like the first half second has passed, we are not actually producing any rows. So this is where you will see where we are actually spending time. And I hope with time someone will make a tool to show a flame graph or something of this. This is that would be cool. This is still a bit hard to read. You have to scan through a lot of numbers, but at least it has all the information you need. And this is always exactly the query plan we are executing because it's a raw dump of that query plan. If we go back to our Doxygen documentation here, you see that the row iterator has a debug string function that we call to get that string that we print in explain. So this is a raw dump of that tree structure in memory. So that is explain analyze. Any questions about explain analyze before I go on to memory profiling?
Maybe just one.
Yeah.
As I understand, explain format tree, there's some statements that are non-explainable in that. Is there anything that's non-explain analyzable? Like, what's the limits?
Yeah, it's the same stuff. So there shouldn't be, since 8.0.20, I think, almost everything, all selects, all queries should be explainable with explain format equals tree. Some updates and deletes might still not be. I think I'll wait for the next versions of MySQL, and you will see even more stuff covered, also for update and delete and that kind of thing. So basically, there are two execution engines in MySQL, one with these iterators, one without them. And we are dumping the iterators. So what we can't explain with tree format is the stuff that we can't execute with that iterator, that executor. But that's almost everything now. The only things I'm aware of that we are not using that executor for is some things that have a special hand-coded fast path through the server that doesn't really go through the optimizer either. So everything that is optimized is now explained with format equals tree. But if in some cases, some things are going through a fast path where it's not actually using the optimizer. It just detected, okay, this is a type of query. We're bypassing even the optimization step because it takes too long. So you're bypassing the optimizer, and then we don't actually produce a plan. We just execute. So that's where you see that error message where you can't explain with format tree, and then you can't explain analyze either.
Awesome, thank you.
Yeah. Okay, I'll try to get through the memory profiling as well. So this is an experiment. I sat down a few days ago and made it work. So this is an experiment. So what I'm going to do is I'm going to execute a query, and from another connection, I'm going to monitor that query as it executes and pull information out of performance schema to analyze the memory usage of that query. So first, I'm going to need the connection ID. So if I go to my session, clear it up, I select the connection ID. This is the same that I get from show process list. I am connection 10. And I know that. And I have a monitoring connection here it's blue. Should be easy to distinguish these two. That's connection 9. So 10 was the one I'm querying in, and 9 is this one I'm looking at. So I'm just going to set the process ID to 9. So I keep it in a variable somewhere. The thing is, performance schema does not work with process IDs or process list IDs, connection IDs. It uses thread ID. So just to make it easy, we have a lot of tables here in performance schema. Threads is one of these tables, and that's the only table I know of that combines the process list ID and the thread ID that is used in every other performance schema table. So if I'm looking for process list ID equals whatever, whatever process I had. So this thread, the client thing I had is number 9. That's thread ID 49. It's just a coincidence that the last digit is the same thing. But I'm going to need this thread ID. So I'm setting the thread ID to whatever I find here. Then I can use that to look into other performance schema tables. I can see what I have here. I have some, I'm looking for memory. And I have some tables here that look interesting. I think I want to go by the summary by thread by event name. Because I have my thread IDs, I'm looking for a specific connection, not a user or from a specific server or globally. I'm looking for one specific thread. So memory summary by thread by event, event name, maybe. So we see we have thread ID, we have event names, whatever that is, and we have various counters for things. And I don't know the details of all these, but I'm looking at this one, which looks like the thing I'm going for, which is whatever amount of memory am I using at the moment. We can look at that for that connection I had. So let's say event name and current number of bytes used from copy paste, where thread ID equals my thread ID, or the other connections thread ID. And there was
again name.
Sorry?
Again name. You forgot underscore name.
Event name, yeah. I not suspected that. So there's a lot of things in here. So these are all the event names. Turns out event name, event name is basically a categorization of different types of memory blocks. So you have, for instance, memroots, different memroots, which are kind of area allocators. You have something for prepared statements. There's something for stored procedures. Quick range select, that's the range optimizer's memory. So this is memory used when we are mapping out ways to do range scan of an index. Various groups of memory here. What I'm going to do is I'm going to focus on this one, not because it's particularly interesting, but because I know how to control this. I know how to generate geometry memory usage. All the other stuff is, yeah, you have to know the details, but this one I know. This is all the memory that's used to store geometries in memory. So I'm going to do a GIS query just because I can control the memory usage. So I'm going to monitor that one. That's my purpose here. So there's one more thing. I'm only going to monitor this when the query is actually running. So what's the table called again? It was threads. So I have a field in this thread that says, where is it? It is process list command, I think. This is the wrong session.
Monitoring
yeah.
yourself. You need to monitor the other one?
I'm monitoring myself, yeah. So let's see, where am I? There, 10 is what I'm looking for. Yeah.
Yeah, the blue is the debug one, right?
Yeah. So pid equals 10, and my query should work. So yeah, the process command then it matches. It says sleep because that connection is not doing anything. But when I did this the wrong way around, it says query, which means that if I start running a query, I can do that in the order one. Select sleep 10. And then I go back and rerun this thing. It says query. Again, it says query, sleep. So it's done. So whenever it says query, there's a query running. So I can use that to kind of monitor the state of that connection just to trigger things when a query starts executing. So I had a small script here, if you can read this. I'm picking out the thread ID, just as I did in my terminal. Then going to repeat as long as it says something else than query. Until it says query, I'm just going to repeat. Then I'm going to repeat until it says sleep again. So if I copy that, that's the wrong window. This one. Wrong database. Try again. There, I can now do monitor connection. I use the process list ID. And it says it's waiting for connection monitoring to start. Then I switch back to this one. I can rerun that sleep thing. We see that it has started. And it's waiting. And it will end. So I can actually monitor this query from the other side. Then we can start actually looking at the memory consumption of this. So what I did was to start logging all the memory users I had. So I had yeah, all these. Actually, I dropped the whole thing, a whole table. Maybe I have it further up. No. What's happening in my terminal? So all this stuff and more, I'm logging every 10th of a second, what I think was my ID. So I just need a query that runs for long enough for me to have a lot of samples. So I have a sample, an easily sampleable query. I can do that from scratch, I think. So there's a function here called buffer that takes a point and produces a buffer around it. So let's say you have a point, and then you create a circle around it. It won't be a circle; it will be a polygon representing a circle. So an approximation of a circle. So this is this is a hex dump because it's a geometry that you can't draw in the terminal. As text, it looks like polygon something. So it's a polygon that has a radius of 1,000. And it has some default number of points depending on various stuff. But I can control that. So I can provide a buffered strategy that is it's called point circle. So we're creating a circle around a point, not a square or whatever. And here I can say that I'm going to need I'm going to want 10 points in that polygon. Or if I add, say, 100 points, you see that this is bigger. So this way I can control the number of points. And I know every point is an X and a Y coordinate. Each one is a double. So there's 16 bytes per point, at least. There's some overhead as well. So by controlling this one, I can control the memory used for geometries. So I'm going to use another feature in MySQL 8. It's the values table constructor. So select I from values row. Wait, it has to be parentheses around this. 1, row 10, row 100, row 1000, row 10,000, and I'm going to stop at 50,000. And I'm calling that derived table ints, and the column is I. So this just gives me a table with these numbers. By the way, I saw some noise on the web about deprecating values in insert on updates duplicate key error thing. This thing is why we are deprecating that, because we have to specify row here because the misuse of values in updates duplicate key things. So it won't go away with immediately. So you can keep your insert statements, but this construct is why we are deprecating it. This is this is standard compliant, but this one should be optional. And that's why we have to deprecate that thing. So for now, you can construct it like this, but in the end, we'll have to do that deprecation and removal to get to making this optional. Okay, but now I have a table with some numbers. And instead of selecting I can select st buffer of 0.00, say still radius 1000. I'm going to need st buffer strategy with point circle and I. So I will, for first row, I will compute a single point buffer. That's interesting. Then 10 point polygon and 100 point polygon and 1000 point polygon, 10,000 and 50,000 point polygons. That takes a few seconds. A few. Prints out a lot of garbage. Okay, it took 5.41 seconds to produce and at least that long to print, I think. So in order to make this a bit slower, I'm going to select sleep for 2 seconds for each row as well. So this should now take around, I don't know, 15, 18 seconds, something like that. And that should be slow enough for me to actually start monitoring this thing as it goes. So I would have a lot of samples as it executes, and in the end I will get a dump. So yeah, almost 18 seconds. So the function I have for this is far down here somewhere. I don't know if you can read that. Larger. So it starts out like the one I had before. I have some extra info here in stage. I'll get back to that later on. So first, I'm just going to create monitoring data, a table consisting of all these columns that I get from the memory performance schema table. Then I'm waiting for the connection to start. This is the repeat. And then when I start repeating this, I sleep for 1/10 of a second. And in between, I'm inserting a dump of this performance schema table. So performance schema memory summary by thread by event name. So I'm dumping the full contents of that thing into monitoring data every time, preceded by a timestamp. So we have a unique timestamp for each dump. So the now function will return a consistent timestamp for the entire transaction. So I could use sysdate or something, but then it would be kind of real wall clock time. But this one is persistent throughout every row of this insert. So just a little trick I discovered while testing this thing. But I'm basically dumping the whole table every time. So there's a lot of data in there. And then when I finish, I just disconnect and do whatever. I have some information here about stages. I'll get back to that later on. First thing, I just had to zoom out a bit and copy paste this thing. So this is not perfect. It has a lot of error messages at the end, but we'll see what it turns out to. Okay, so there seems to work. And I can try to monitor my connection. So now I'm just waiting for the other one to start. I'll go back there, and I'll start it again. This one is not interesting, so let's watch the monitoring. Starting, and this will be going on for a few seconds. So it took almost 8 seconds from I started this one until it started executing on the other connection. So this 8-second thing will pop up again in our logs. So yeah, this is the stuff I'm talking about. This is not perfect. But if I scroll up, I have some stage stuff that I'm going to talk about later. But we see it's waiting for connection 10. Started, it ended, and yeah, I'll get back to the stage stuff. So now I have this monitoring data thing. That's a lot of stuff. You can zoom out. It's a huge table. And I have a way of reducing that data. So I have here a query that selects only this geometry stuff and dumps it to a CSV file so I can graph it in LibreOffice. That's the easiest way I found to do this. So back to my monitoring thing, I'm just going to execute this query. So I also do some magic with time. I'm taking timestamps. I'm computing a relative time instead of wall clock time. I'm doing relative time to the query execution. So this will dump things into a file. 171 rows, so 171 samples in this thing. So I have. I'm sorry about the column and font sizes here. That's it's LibreOffice. I can't do much about it, I think. But my CSV file opens easily. So I have wall clock time. I have relative time. I have the amount of memory allocated to geometries and the total amount of memory allocated at each point. So you see I have relative time 0. That's when I started the procedure. 7.6 is, I think, around when the query started executing. So just remember that that's a problem in this data set. Going to insert a column. I'm going to call this one other. That is the total, and we subtract the geometries. We can get all the other memory. And just copy that thing down here. And we see at the bottom that geometry memory goes down to 0, which is a good thing. We actually free the memory we allocate. There are a few weaknesses in performance schema. That means that sometimes memory is freed by a different thread that allocated it. And that makes for some funny numbers. But for geometries, at least, I don't think that's the case. So this one should be safe. So I'm just going to go through like this and do a graph. Here a graph. And this one is normal, but I want it stacked. So it stacks and gives me the total at the end. And first column is label. finish, and let me zoom in on that thing for you. This is our graph. So we see the blue one is other. It increases a bit and then it drops at the end. But the geometries, they keep growing and it has some spikes here that I'm curious about. So this is the actual geometry memory that I'm using. And the largest one was 50,000 points times 16 bytes. It's around, I don't know, 800,000 bytes, something. We see we peak here at around 3 megabytes for this query. But more like 2.5 here. But we are keeping, remember, we are keeping not only the largest one, we are probably also keeping some of the smaller ones at the same time as the largest one. So this is not unexpected. What is unexpected is this one. So I don't know what this one is. But it might be something we figured out that, okay, we can drop stuff and we finally just deleted or freed that memory. Maybe that row was copied over to the client and we could now drop the data or something. Could be that. It could be dependent on the actual protocol sending this over to the clients. I honestly don't know. This is the first graph I ever produced in this one, and this monitoring is new to me as well. So we can produce graphs like this. We can add more event names and add different types of stuff here. It would basically take this blue line and divide it up into smaller parts. But in this query, at least, the geometries are dominating by far the stuff. I promised you something about stages, and I'm going to show you a little bit here. I printed it here, but I also dumped it to a table. Monitoring stages. So this is a table called performance schema. My notes somewhere. Stages. Oh, let's see. Oh, yeah, there it is. The table is called Event Stages History Long. That's the name of the table in Performance Schema. So I just dumped that. I cut it off. I use some magic to find the start of this query and the end of the query. So I get the relative time here. But this is relative to the query start, so it's 8 seconds off from the other counter I had. But we see that these phases are not always easy to read, but execution, first time it's mentioned, is after 0.0002 seconds, so almost immediately. And then end is where we finish this query, is after 17.64 seconds, which is almost at the end of the whole thing. So almost everything, almost all time is spent in execution. User sleep is part of execution. This is what we call the sleep function. So that's where we spend most of the time, actually. But this one represents query execution. So from 0 point something till 17.64, we are actually executing query. We are evaluating rows. And actually, when we call these iterators, one of them will be evaluating sleep. So there will be a call to the val function on sleep, the evaluation function on the sleep implementation. And we'll just sit there waiting for 2 seconds until that iterator returns a row again. So if we try to match this with our graph, we'll see that, OK, we start executing maybe around here somewhere, and we end execution around here somewhere. So all this stuff is during execution. So we see that to begin with, actually, the geometries don't register at all. The first one was very small. The first few were very small. That could be one of the things. I see some orange thing here. So maybe there's another orange here and one here. It would take a few seconds for each of them. But also there could be some startup here on starting execution. I guess that would be around this corner here on the graph, where we actually, for instance, generate a plan and start running things, allocate some buffers and whatnot. but yeah, that's basically the stuff I had. This is, as I said, experimental. I've been thinking about this for a while, and I finally got around to writing a script for it. And I have to play around with it a lot more before I can say if it's really useful. But these things, for instance, caught my eye. I had another graph earlier where I had only one of them, so I'm curious what it is. That's something I will start looking into.
Norvald, just a 10-minute to the top of the hour warning.
Yeah, I'm basically done. I've shown you what I wanted to show you, and
Awesome.
there's a lot of more to look into. But people can ask questions. We can try to run a query or two. But yeah, this is my experiment, my fun little experiment.
I'm sure I could ask some questions, but I'll let others ask questions first. Make sure they get a chance.
If people are shy, they can also type the question on the chat, and we're gonna read it to Norvald.
All right, I'm going to go first. Norvald, I assume because the temporary engine now uses a shared pool, it probably won't show up here.
Yeah, that could be the case. Not in this graph, at least. It should show up in this blue thing. Or, no, buffer pool is not there. Buffer pool is not in part of this one.
Because you've got like the thread statistics here rather than what are we allocated to different.
Yeah. So the shared pools are not part of this. So this is all the memory that can be allocated to, or kind of we can blame on this single thread. So you see there's a bottom line here, where like 250,000 bytes. That seems to be there always. I'm not sure what it is. It's I guess session state variables. Maybe the previous query run, like there is some information kept around some state.
We could see it was in there.
Yeah, we can look at it. It's just so hard to look at.
I was going to suggest, well, you could do it just on
just keep talking.
So when you said as well query end or end, that's when rows are sent to the client, right? And then the other stuff happens asynchronously, like removing temporary tables, logging.
Yeah. So, well, temporary tables are part of buffer pool, as you said, so that won't show up here. But as memory, like when the protocol transmits data over to the client, there's going to be a packet in memory that we are going to ship off, and when that one has been sent, it's freed on the server side. So for these geometries, for instance, they are quite big. So I would expect some asynchronous freeing going on there whenever one of these huge packets are sent. So yeah, and I would expect to see that in this allocate this thread. I'm not sure if it's in this thread, but I would assume so.
Okay, and then just filter it and say where the allocation is greater than 0.
Yeah, okay, I can yeah. And I think the current one, what was it called? It was I have to do my cheat sheet. Current number of bytes used.
That's right.
Yeah. Larger than 0. Okay, zoom in. All right, string, THDDB, variables. Okay, this is the current one. This is not from the history. I can.
That's all right. I think it'll actually be fairly close because you were doing the initial size.
Yeah, the initial one should be this one. Yeah. So InnoDB memory. So H and InnoDB should be some parts of the handler interface. I don't know what is stuck to this thread though. THD variables are session variables. I have like some user variables, but I also have all these system variables that I can set that are already there.
Because it has to clone them from the global.
Yeah. Yeah, so the global system variables are the default values, and then you clone them into each session. And string is a I guess everything is a string. Or every string that we store is counted like this. If it's part of a row, if it's part of a system variable, if it's part of whatever. So it's a bad grouping, but it's there. I can. By the way, I could.
As well, if there are no other questions, I have another one.
Yeah.
How accurate are the stages? My understanding is they're not entirely accurate. Like sorting gets blamed too much. And what's your commentary there?
Yeah, I think maybe sorting is out of this now. The problem with stages is that they are not actually stages. They are kind of the task currently being executed. So you saw this. You see this user sleep. User sleep is not a stage. It's a task being done at the moment. Executing is a stage. Preparing is a stage. Optimizing is a stage. But all these other ones are just stuff that's happening while we are in the executing stage. There's some things here like, okay, this is not sorted because some of these values should be the same, I think. Preparing shouldn't happen after optimizing, for instance. So I haven't looked at the numbers, but let's see if this order by timer start, it changes. No, it doesn't. So something is stranger when preparing after optimization. But I hope we can get to a point where we can, there's a hierarchy here, right? So I hope we can get to a point where you have preparing and different sub-steps of preparing, but that we actually do that. But execution is going to be one step, I think, in the end, because we are pulling row by row. All the stuff, all the sorting, all the materialization stuff, it happens as we pull rows through that iterator tree. So it's not really a stage. So I think we removed the sorting stage because it didn't make sense. In the end, I think it's it's just something that happens while we're executing. So yes, I think we'll have to, if we start using this, we have to look at more into what's going on here and what we're actually doing.
Have some of these stages changed lately? I seem to remember that earlier that most of the time was spent in sending data, but that is not shown here.
I think we might have removed sending data as a stage. I'm not 100% sure, but when we did the refactoring for the iterator execution thing, we did remove a few stages or in work related to that. So some of these stages have been changed, yes. I'm not sure about the sending data, but sending data was a one stage. But it might also be that we just do so much sleep in this query that we don't hit that one. Mm-hmm. I'm not 100% sure.
But now that you have the analyze information, wouldn't that be more useful than these stages?
The analyze information will show you everything happening here. It does not show you optimization. So if preparing and optimizing took time, spend some time doing things,
yeah,
it would show up here. And that's where I'm hoping we could get some information out of this one. And also all this cleanup afterwards, that should be fast. But if it isn't, then it should show up here, not in analyze. Because mm-hmm. when this happens, analyze is already done. It has returned its results.
Makes sense. Norvald, we're at the top of the hour, so I'm going to turn off the recording. But if you don't mind staying around for a couple more minutes.
Yeah, sure. I'll hang on.
Okay. Thank you very much. It was very entertaining.
Thanks for listening.